All right, we'll get started. So yeah, fill out the attendance. I posted homework 4. I know you guys are still, some of you, or a lot of you are still finishing up homework 3. That's due on Friday. Homework 4 has now been posted, and it will be due a week from Friday. Okay. I do think working on homework 4 will be helpful in preparation for the midterm exam. So we have all right. So there, you guys. We have a midterm on Monday, right? 7th week Monday, and I think that's what I have written, right? Okay. I'm not making this up. Okay. So we've got a midterm 7th week Monday, and I'll talk about a little bit, more of the details on Friday. But I will say, I think starting homework 4 and at least trying to work through those problems there will be helpful in the preparation for the midterm exam. Okay. Do we have any questions before I get started? No? Yes.
Monday's meeting will cover until this Friday.
I would say Monday's midterm will probably cover up through like today's stuff. Okay. On Friday I'll do so far we've been doing like Metropolis algorithm. Today we'll do the Metropolis Hastings algorithm, which is just a small modification of it. And then I'll try to explain detailed balance and show that it satisfies this thing. On Friday, we'll do a kind of a neat little application of the Metropolis algorithm, which I think is pretty cool. I don't know, we might not get through the whole thing. Well, maybe we will. We'll see. I'm excited to show you. We'll see if you guys are impressed or not. Okay. Yeah, so midterm on Monday. Okay. Here in this class, and I'll do another seating chart and everything. So, okay. Let's see. All right. So let's talk about the Metropolis Hastings algorithm. So the Metropolis Hastings algorithm, it's very similar to the Metropolis algorithm, except the proposal distribution does not need to be symmetric. Okay, so very similar to the Metropolis algorithm. Except the proposal distribution does not need to be excuse me, need to be symmetric. So in Metropolis, you have some proposal Q, some proposal distribution Q, and for the symmetric part meant that the probability of proposing x prime, given that you are currently at xk, has to equal the probability of going the other way, xk, given that you are at this value. Okay, so the probability proposing x prime if you are at xk must equal the probability of proposing xk if you are at x prime. Okay, that's what it means to be symmetric. Now, with the for Metropolis Hastings, basically this requirement is removed. Okay. Okay, and so, generally textbooks will often talk about the Metropolis Hastings right away, and then they'll throw in a footnote that says, oh, but it's symmetric, so it becomes a Metropolis algorithm. That's all that we have. Whoops. Okay, so basically, so in the Metropolis algorithm, if you have kind of x prime here, I'm sorry, xk, and you have like a normal distribution, and you might say, like, what is the probability we will propose x prime? Well, that probability is right there, okay? And likewise, if we're centered at x prime, it's hard to draw. I don't know how to draw this thing, okay? Basically, the idea is, okay, well, what's the probability of proposing xk? They're at the same height, okay? The idea is these two probabilities are at the same height, okay? My picture's not perfect, but that's kind of the idea. All right, and then in Metropolis Hastings, or in the Metropolis algorithm, one example was we had the coin flip, and so we had a 50% probability of proposing going to the right and a 50% probability of going to the left, which means, I have a 50% probability of proposing island 5 if I'm at island 4, and that means if I'm at island 5, I have a 50% probability of proposing island 4, okay? So, for the Metropolis Hastings algorithm, some examples could be maybe an unbalanced coin. So you propose, I don't know, theta plus 1 with probability equal to 0.7, and you propose theta minus 1 with probability equal to 0.3, or something like that, okay? Or another example could be, you're centered at xk, and I don't know, you've got this funny looking distribution or something like that, and you'll draw x prime coming from something that looks like this, okay? Just something that's not even, okay? Some non-symmetric proposal. All right. So, I mean, that's the difference between Metropolis Hastings algorithm and Metropolis algorithm. And basically, if the proposal distribution is symmetric, and we often like to pick symmetric ones because generally they're, I don't know, easier, but they're nice to work with. then it becomes just the Metropolis algorithm. So if you have the normal distribution as a proposal, then it's just the Metropolis algorithm. Okay, so that's all. And I just, so let me explain the detail out the steps, okay? So the steps in the MH algorithm. All right, and then so we'll say for each iteration, we'll say k from 1 to 2 to n. What you will do is you sample your proposal, sample a proposal value. I'm not feeling that great either. Yeah. All right. Sample a proposal value from, your proposal distribution Q. Okay. So you'll from x sub k. All right. So you have proposal distribution Q. And then 2. Find the acceptance ratio, which is going to be equal to the minimum of between 1 and this is where it differs, is that you've got the probability of x prime divided by the probability of your current x, xk, times, and then you have kind of the difference between the proposal rates, okay? So this is, the probability of proposing k if you're at x prime and the probability of proposing x prime if you're at xk, right? So you have this. So this is how it changes, okay? And then, sample u from uniform 0, 1, and then accept x prime if u is less than the ratio, and then xk plus 1 will equal x prime, or reject x prime if u is greater than the ratio, which means xk plus 1 will be your current value of xk. And that's the Metropolis Hastings algorithm. Okay, so I wanted to take a little bit of time to kind of, I don't know if prove is the right word, maybe just demonstrate or show that by having the Metropolis setting up kind of our transition probabilities this way, the Metropolis Hastings algorithm will converge to, or that the stationary distribution of the Metropolis Hastings algorithm will converge to your target distribution, okay? And then obviously if the Metropolis Hastings algorithm converges to the target distribution, then the Metropolis algorithm, which is just a special case of this, will also converge to the target distribution, right? So I hesitate to use proof because proofs are generally a lot more rigorous, okay? So we'll try to demonstrate that if we set up transition probabilities according to the Metropolis Hastings algorithm, then the stationary distribution of the Markov chain will equal the target distribution. And then, which means that if you allow the Markov chain to run forever, you know, the values drawn from the Markov chain will converge to its stationary distribution, which is the target distribution, which is what we want, right? So if we let the chain run for a long time, it will converge to the stationary distribution, okay, which is this is more a result of the kind of ergodic theory that says if it's aperiodic and irreducible and whatever, there's this happens. Okay, so basically we need to show that the detailed balance condition is satisfied by the Metropolis Hastings algorithm, okay? So basically that if we set up our transition probabilities this way, it will satisfy the detailed balance condition, okay? So basically we need to show that if we set up transition probabilities this way, it will satisfy detailed balance condition. Okay, so what is detailed balance? It's the idea that, if we think back to the island, okay, the island nations, the people going from island 3 to island 4 is equal to the people going from island 4 to island 3. Okay, that's basically it. And so the detailed balance, so we'll say T of xk plus 1 given xk times the probability of xk is equal to T times T of xk given xk plus 1 times probability of being at xk plus 1. Okay, this is the detailed balance. Okay, so this is transition probability of going from xk to xk plus 1 times the probability of being at xk, right? This needs to equal the transition probability of going the other way. Xk plus 1 to xk times the probability of being at xk, right? So this is effectively saying that, the number of people, or the total probability of going from, one state to the other state is equal to the going from that state to this state, okay? So going from basically state A to state B is the same as those going from state B to state A. Yes? Oh, probability of being at xk plus 1. Thank you. Thank you. Yes. Okay. All right. So let's take a closer look. Is that all right? Okay. And so we will do. Okay. So in the MH algorithm, we will propose an x prime, okay, and then and it's possible. So there's two possibilities, okay. We propose an x prime, and we have two possibilities. Okay, and one is we reject x prime, and xk plus 1 is equal to our xk, right? And two is we accept x prime, and xk plus 1 is equal to x prime. Okay? All right. So in the first case, in the first scenario, where we reject x prime, then xk plus 1 is equal to xk, right? And so it's trivial to show that detailed balance here is satisfied, okay? Because xk is equal to xk plus 1. So to show that the transition probability of going from, what do they need to write? Xk plus 1 given xk times the probability of being at xk is equal to transition probability of xk from xk plus 1 given that you are at xk plus 1. Well, everything the xk plus 1 is equal to xk, so this just becomes the transition probability of xk going to xk given that you are at xk times the probability of being at xk, which is equal to the transition probability of going to xk given that you are at xk, which is equal times the probability of being at xk, right? So this is a trivial case, right? Because xk plus 1 is equal to xk, so it's saying, like, is the number of people that go out and come back equal to the number of people that came in from going out? Yes. Okay, that's it's balanced, right? If everybody just returns to the same state, then we're at balance, right? So we really just need to show that this detailed balance holds when xk plus 1 is different from our current xk. All right, so let's take a look at this. Okay, so what we have is we have the transition probability of going to xk plus 1 given that we are at xk. This is equal to the minimum of 1 times the probability of xk plus 1 divided by the probability of xk. So our proposed value given times our current value times the proposal distribution, xk given xk plus 1 times probability of xk plus 1 given xk. So this is the acceptance probability, and then the transition probability is, well, we have to accept it, but first we have to even propose it, right? We have to, I'm sorry, and this is a Q. So this is basically saying the probability of going from xk to xk plus 1 is equal to basically the probability of proposing xk plus 1 if I am at xk times the probability of accepting it. Accepting the proposed value. Okay, and then we'll expand, kind of do a little bit of multiplication here, all right? And so this will become, I'm going to pull out we're going to have 1 over the probability of x sub k. Here, I'm going to close our attendance poll. Close the poll. Times, and this is the minimum value between, and if I distribute kind of this multiplication here, okay? So this cancels out the bottom, and it's just the kind of the top part here, okay? So 1 is going to be the probability of xk times q xk given xk plus 1, and the minimum probability of xk plus 1 times q times xk given xk plus 1. Okay, so basically I have 1 being p of xk over p of xk. Is that okay? This step. Okay, so that's the transition probability of going from xk to xk plus 1. Okay, if using the same logic, if I flip everything around, okay, so using basically the same logic and reasoning, then the transition probability of going from xk given from xk plus 1, this is going to be equal to 1 over the probability of x. So I'm just basically switching symbols here. Minimum between that and the minimum of did I do this correctly? I just switched x where'd it go? Okay, sorry. So I'm just switching the letters for this, okay? So just wherever I saw xk, I gave xk plus 1, and wherever I saw xk plus 1, I replaced it with xk. Right? Is that okay with everybody? All right. And what we notice is that this term and this term, these two terms are exactly the same. Oh, wait, no. Hang on. No, they are not. Sorry. Just keep jumping ahead of myself. Okay, and so all right, so let me copy this over onto our next slide, just so I can kind of keep track of everything. Did I make a mistake somewhere? Let me just verify my notes here. K plus 1 given that, x, k plus 1 given x. Hold on, sorry. Probability of xk given, oh, I made a mistake. Oh, I hate it. Okay. I sincerely apologize. I made a mistake back here. Okay, so this is xk plus 1 given x of k, and that changes this. Okay, let me just verify. There's so many little symbols, right? So it's the minimum between this, and the minimum of this times this, and this, and this times this, and this. Okay. Okay, yes. So we're distributing this thing across the things. Okay. All right, I apologize. Okay, now I think my symbols are correct. Yes.
In the first line, why did you multiply by q on the outside?
So it's the probability of proposing value k plus 1, given that we are at k, times the probability of accepting the proposed value, which is going to be the minimum between 1 and this acceptance ratio. Is that okay? All right, and then if I distribute, if I replace 1 with basically probability of xk over probability of xk, okay, which is 1, and I distribute this xk plus 1 over here, then I have probability xk times q xk plus 1 over given xk, and then over here for the second term, this will cancel out with this, and we will be left with this part. Okay? All right. I think I can keep going here. Let me just shrink this down a tiny bit. Okay, so we have that, and then so what we have is we need to show that the transition from k plus 1 going to k plus 1, given that we are at xk times the probability of xk, so this being our detailed balance condition, this is going to be equal to this whole thing times the probability of xk. So I'm going to have probability of x of k times, I'm going to go ahead and just cut and paste this thing, okay? Is it okay? Okay, so these will cancel out. All right, and then if we look at the other one, xk, given that we are at xk plus 1 times the probability of xk plus 1, this will equal the probability of xk plus 1 times 1 over, well, I'll just copy this, all right? Nope, that's not it. Okay, and so we have this, and then yes. What we notice is that this term and this term are exactly the same, right? So this whole thing, this thing is equal to this thing, and this thing is equal to this thing, all right? So the minimum value between this and this and this and this, right, is going to be the same. So so the transition probability of going to k plus 1, given that xk plus 1, given that we are at xk, times the probability of being at xk is equal to the transition probability of going the other way. Xk, given that we are at xk plus 1, times the probability of xk plus 1. So these are equal and these are equal, so. Okay, and so which means so detailed balance is achieved when we use the Metropolis Hastings to we use Metropolis Hastings to determine transition probabilities. Is that okay? Are there questions on this? Okay, so this is just kind of a demo to, well, not a demo, just trying to show that we end up getting the detailed balance by this, and that's why the Metropolis Hastings will work if we set up our Markov chain this way, so that it will, the stationary distribution of a Markov chain that uses the Metropolis algorithm or Metropolis Hastings algorithm will converge to the target distribution. Okay, are there any questions? Okay, you know what? With a couple minutes left, I'm going to do a physical roll call, so we'll just make sure. Nobody like walked out mid-class, right? I didn't notice anybody walking out. Okay, so we'll